Hello, this is Joseph Domingo. Here we have the language of mathematics. In this part, we are going to be talking about the truths and implications. So, here we have the truth values. These are essentially if P and Q are true or false. So, P can be true or false. Q can also be true or false. Now let's talk about the connectives. So, first we have conjunction. If P and Q is true, equals true. If P and Q is false, it will be false. However, if one of them is false, it will be false. So in here, in the table, we have P and Q being true, it will be true. We have P and Q being false, it will be false. However, in here we have P equals true and Q equals false, meaning it will be false. Next we have disjunction. If P and Q are false, it will be false. If either one is true, it will be true. So as long as there is a true in P and Q, it will be true. The only way it will be false if both P and Q are false. Next we have exclusive. If P and Q are false, it will be false. If P and Q are true, it will also be false. However, if P and Q are different from one another, it will be true. So if P and Q are the same or both are true or false, it will always be false. However, if they are different from one another, so P is true or Q is false, it will be true. Here we have implication. Now, since P is implying Q, if P is true and Q is false, it will be false. However, if P is false, it will be true. So, if P and Q are both true or false, it will be true. However, regardless of the truth value, if P is true or Q is false, it will be false. However, if P is false and Q is true, it will be true. Next we have biconditional. If P and Q are true, it will be true. If P and Q are false, it will still be true. However, if they are different from one another, it will be false. So here we have P is true and Q is also true, it will be true. P is false and Q is false, it will still be true. However, P is true and Q is false, it will be false. Same thing if P is false and Q is true, it will still be false. Next we have this symbol. It means not, which means the opposite truth value. So if P is true, not P will be false. If P is false, not P will be true. So in this table, we have not P and truth values that has not been converted yet. We will need to convert that, meaning true will become false, false will become true, false will become true, true will become false. And with that, we can now solve the disjunction of P and not P. So true and false will be true. P is false and not P is true, it will be true. P is true and not P is true, it will be true. P is false and not P is false, it will be false. Here we have compound propositions. Essentially, we have two propositions and we need to find the truth values of them. That is denoted by a connective. So in this case, we need to find the exclusive of P or Q and not P or Q. So we're going to be separating this to multiple parts. We're first going to be finding P or Q, or the disjunction between P and Q. That will be true and true. Next, we're going to be finding not P. So the opposite of these truth values, it will be T and F. Next, we're going to be finding not P or Q, which means that we're going to be using the values of this and compare it to this in order to answer this question or this proposition. So if we do that, we will have false and true. And then after that, we can now solve the exclusive between these two propositions. which would mean we will have true and true. Next, we have the different kinds of compound propositions. If the compound proposition is true, it will be a tautology. However, if it's false, it will be a contradiction. We can see here that it is both true, so this whole table is a tautology. If these were to be false, it would be a contradiction. Next, we have the logical equivalence. This basically means that in a biconditional, the two propositions are the same. However, in this example, we can see that the two propositions are not the same because we have true and true, but in the other proposition we have false and true, meaning they are not the same and therefore it is not equivalent. If if this truth value were to be true, it will be logically equivalent instead. Next we have the contingency, which means the compound proposition is neither true or false. If we look over here, one is false and one is true, meaning there's a contingency, it is not the same. Next, let's talk about the implications. So in this implication, P implies Q. P is the hypothesis or the antecedent, and Q is the conclusion or the consequent. Meaning, in this example, if today is Monday, then I need to go to the mall. P will be if today is Monday, and Q will be then I need to go to the mall. P is the hypothesis, and Q is the conclusion of that hypothesis. Next, we have the converse. This means that P implies Q is not the same as Q implies P. So if today is Monday, then I need to go to the mall. It is not the same if I say if I need to go to the mall, then today is Monday. Next, we have the inverse, which means it is the inverse of that implication, which would mean that if P implies Q, and we're gonna have to find the inverse of this, it will be not P implies not Q. An example of this is if today is Monday, then I need to go to the mall. P is if today is Monday, and Q is then I need to go to the mall. If we're going to inverse this, it will become if today is not Monday, then I don't need to go to the mall. Next, we have the contrapositive. This means that two implications meaning the same thing. So if we have not P implying not Q, it is the same as finding the biconditional of P implies Q and not Q implies not P. So an example of this will be if today is Monday, then I need to go to the mall. If I don't need to go to the mall today, then today is not Monday. They mean the exact same thing. And that's it. Thank you for listening.